Okay, come on. There we go. So sorry about the lack of desks. I don't know what happened. Before the semester started, we got an email saying that CFA 101 had a furniture issue. Like it came in the first day and it was fine. And apparently now the furniture issue has manifested itself. But I think we'll be okay. So today's molecule of the day is urea. There's the structure of urea. As you might be able to tell, the root of urea is the same as the root of urine, and that's not a coincidence. It's a pretty important human waste product, specifically in regards to the nitrogen atoms. And that's one thing you'll notice about this molecule is it's got a pretty high ratio of nitrogen to other things. Because of that, it's very useful as a fertilizer. Nitrogen is sort of like the fertilizer atom or the fertilizer element. And because urea is so easy to get and so cheap, it is often used as a fertilizer. And it's an important industrial precursor, as are a lot of small molecules like that. So the last thing we talked about was formal charges. Do we have any missing formal charges on my drawing of urea? Anybody see one? Good. I like the silence because there's no formal charges. All of the atoms in this structure are happy as they are. The nitrogens both have 3 bonds and 1 lone pair. The carbon has 4 bonds. One of them's a double bond, but 1, 2, 3, 4 bonds total. Oxygen has 2 bonds and 2 lone pairs. Again, it's the 2 bonds are together in 1 double bond, but that's okay. And then the hydrogens all have 1 bond, and so they're happy. Okay. So the next thing we need to talk about is hybridization. And in order to do that, we need to remember back to electron configuration from Gen Chem. And that's the thing where it's like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, et cetera, et cetera. And sorry, it's the 6. As you go along the periodic table, going from element to element, you add an electron and you keep filling up this configuration. So for our elements, and when I say our elements, I mean the ones that are really relevant to organic chemistry, like carbon, nitrogen, and oxygen. Two S2 and 2p6 are the valence orbitals. And so those are the outer shells that are the furthest away from the nucleus. And so those are the ones where chemical reactions take place. And those are the electrons that move around and do the interesting stuff. 2s2, 2p6, at least when they're full. So that's a total of 8 electrons, which is an octet. So that's kind of how we get our octet. It's from those 2 orbitals. So one of the problems with this representation is that we've got so that total of 8 electrons is across 2 different types of orbitals. the 2s, and the 2p. I don't know if you remember the shapes of the orbitals, but the s is like a sphere, and then the p is sort of like a figure eight hourglass kind of shape. That doesn't matter immediately for our purposes, but the important thing is that they're different. So if we used that description to talk about orbitals, then that means that 2 of the electrons are going to be in the s orbital, and 6 of them are going to be in p orbitals, 3 different p orbitals. And so what that would look like in an energy diagram is this. There's 3 2p orbitals, and they're higher in energy than the 2s orbital, and there's just one 2s orbital. Okay, that sounds great, but then we look at a molecule like CH4, methane, and you can draw this in slightly different geometries, but you can kind of look at that and tell that all of the CH bonds are the same, right? And we can also use spectroscopic methods to look at methane and see that all of those bonds are in fact the same and all of the hydrogens are the same. So if we've got electrons in our orbitals like that, 3 in the 2p orbital and 1 in the 2s orbital, that would imply that one of these bonds is using a 2s orbital on the carbon atom, and the other 2 are using 2p orbitals. But that would make sense because those are different orbitals, the bonds are going to be different, and we know that isn't the case. So what we've got to do to solve this, and this is all, of course, everything in chemistry is just representations or mnemonics for what's actually happening. So what we do to satisfy this is merge the s and p orbitals and make hybrid orbitals. So we take this, let's cheat there. Right, and so a hybrid is just sort of an average of two things or a combination of two things. And so what we get when we hybridize one s orbital and 3 p orbitals is we get sp3, because there's one s orbital, 3 p orbitals. It's kind of like variables in math. And we have to conserve the number of orbitals, which in this case is 4. And so when we hybridize the s and p orbitals, in this particular case, we get 4 sp3 orbitals. And those are all the same in energy. And so that satisfies the fact that all of the CH bonds in methane are the same. So let's make a summary of the different types of bonding environments that we can find around carbon. So the one we've talked about here is 4 bonds. When we have 4 bonds to carbon, we're using the s orbital and all 3 of the p orbitals. So we hybridize those 4 orbitals to become sp3. An example of course, is methane. We just talked about that. We'll get to length and strength in just a second. If we have something like this, here both of the carbons are identical to each other. But if we have something like this where the carbon has 3, well, if the carbon's still got 4 bonds, but it's only bonding in 3 different places. So in this case, this double bond in between is only using 1 hybrid orbital. And so instead of sp3, we combine 1 s orbital with just 2 of the p orbitals. And so that becomes sp2 hybridized, and carbon has 3 bonds, or 3 things attached to it. We can also have the case where there's just 2 bonds to carbon, or just 2 things attached to carbon. A triple bond, that's acetylene. And it might not surprise you to find that when carbon only has 2 of those bonding domains, we need 1 s orbital and 1 p orbital. And that hybrid is just sp. So how do we figure out the length and the strength of these bonds, at least relative to each other? We can look at the proportion of s-ness and s character and p character, should I say, of the orbitals. So an sp orbital is half s and half p. The s orbital, right, is the sphere, and it's really close to the nucleus. It's really small. The p orbital is somewhat bigger, and the electrons in that case are further away from the nucleus. So comparing an sp orbital to an sp3 orbital, this sp3 orbital has a lot more p character, and so generally the electrons are further from the nucleus than in an sp orbital. So if electrons are further from the nucleus, that probably means that the bonds themselves are going to be longer. And then, well, longer bonds are weaker because the things are further away from each other. So sp3 carbons make the weakest bonds. sp carbons make the strongest bonds. So the main thing you need to be able to identify is kind of these two. I mean, well, it kind of all goes together, but these 2 columns. You need to recognize that when you've got a triple bond going on, those carbons are going to be sp hybridized. When you've got a double bond like this, you're going to have sp2 hybridization. And when there's no multiple bonds going on, you've got sp3 hybridization. As with everything in chemistry, there are exceptions to that rule, but that's what we're going to see most of the time. Okay, so this number of bonds to carbon, I really should call this the number of electron domains on carbon. And that's going to help us for the next thing we're going to talk about, which is VSEPR theory. And that's going to relate directly to the geometry of those molecules that we just talked about. Okay, so VSEPR stands for valence shell electron pair repulsion. And the nice thing about this name is it tells you almost everything you need to know. Valence shell, so we're just talking about the valence electrons, the outer electrons. Probably not a big surprise. Electron pair, okay, so we're talking about pairs of electrons, either lone pairs of electrons on atoms or pairs of electrons that are making bonds. And then the most important part is the repulsion. So the overall theme of VSEPR theory is that everything around a central atom wants to get as far away as possible from everything else. And I think that makes sense if you think about the fact that we're just talking about electron pairs here, not nuclei or anything. Electrons are negatively charged, and like charges repel. So generally speaking, electrons want to get further away from each other, and that means that if you've got 4 bonds to a central atom, those 4 bonds are going to get spread out as much as they possibly can. So we're going to make another table here. So let's do methane, CH4. So there's our Lewis structure for methane. We need the number of electron domains around the central atom. In this case, the carbon has 4 bonds and no lone pairs. So it's got 4 electron domains. Based solely on the number of electron domains, we can associate that with a specific electron domain geometry. So what is 4 in electron domain geometry? Starts with a T. Tetrahedral. So the difference between electron domain and molecular geometry has to do with the presence or absence of lone pairs on the central atom. In this case, we don't have any lone pairs. And so the electron domain geometry is going to be no different from the molecular geometry. So it's also tetrahedral. So that information, specifically the molecular geometry, allows us to draw a 3D structure, which is a Lewis structure that has, obviously, that has 3D information and is usually drawn in a slightly different configuration. And the way I'll represent it is like this, with a wedged bond representing the hydrogen coming toward us, so out of the screen. And this hashed bond representing a hydrogen that's back behind the screen. So rather than being flat and square looking, like the Lewis structure we usually draw, methane is not. It's more like a tripod kind of thing. And you can do some math and figure out exactly what position each atom needs to be in to have the lowest amount of energy. And you can calculate the energy of methane if it looked like that. But there's more distance between each of the hydrogen atoms when it's tetrahedral like that. Okay, NH3, ammonia. There's our Lewis structure for ammonia. How many electron domains does the nitrogen have? 3, right? So it's got 3 bonds and a lone pair. So that's a total of 4 electron domains. The electron pairs, the lone pairs count in this case. So we've already established that 4 is tetrahedral. And that's the case for the electron domain geometry, but the molecular geometry now is going to be different because we have lone pairs involved. So the molecular geometry is just the shape of the hydrogen atoms around the nitrogen. Not necessarily ignoring the lone pair, but taking into account the fact that the lone pair is not an atom. Do we know what the molecular geometry is for ammonia? True, trigonal pyramidal. And so I'm going to cheat and copy this. So how do we turn this into ammonia? Well, obviously we got to replace the carbon with a nitrogen. And then all we do is remove one of the hydrogen atoms and put our lone pair. So it's the same shape, just minus 1 atom. Technically, the angle is slightly different, but it's the same thing, basically. There's no law that says you have to take off the one at the top. You can pick any of the hydrogen atoms to remove because they're all identical. I'll do these last two a bit more. Actually, well, not the last one, but this one also has 4 electron domains, 2 hydrogens, and 2 lone pairs. Tetrahedral, and this one, the molecular geometry is bent. Water is the Mickey Mouse molecule. And so it looks like that. Or another way I could have done it is to take, right, the electron domain geometry is still tetrahedral. So I can copy and paste our tetrahedral thing here, remove 2 of the hydrogens, make this an oxygen, and put lone pairs there. Okay, so these are, I mean, not boring, but methane's an organic molecule. But what about like organic chemistry looking molecules. So for that, our example is going to be formaldehyde. Maybe this should have been our molecule of the day. Oh well. Common preservative, even if it is kind of toxic. Okay, so, well, really, we could talk about the oxygen or the carbon atom and do geometries for both of them, but let's just do the carbon. How many electron domains does the carbon atom have here? It's not 4. 3, because the double bond counts as just one electron domain. So the electron domain geometry is going to be different because the number of electron domains is directly related to the geometry, the electron domain geometry. And 3 is trigonal planar. Don't get pyramidal and planar mixed up. We have no lone pairs on the carbon. And so the molecular geometry is the same, trigonal planar. And fortunately, planar means flat. And so this is actually a perfectly good 3D structure for formaldehyde. We don't have to do anything to it. Doesn't need wedges or dashes or anything like that. So the angles between the oxygen and the two hydrogens are, in this case, 120 degrees. Do you remember what it is for tetrahedral? 109.5? Is that number ring a bell? Okay, so that is Vesper theory in brief. So the formaldehyde and the methane example are two of the more common sort of structures we're going to see in organic chemistry. And maybe the single biggest takeaway from this, at least in relation to carbon, is that when we've got an sp3 hybridized carbon, like in methane, it's going to be tetrahedral. And formaldehyde, this carbon is sp2 hybridized because it's got that double bond. So it's going to be trigonal planar. Yes.
The 3 for
the electron. Yes. So for the methane example at the top, carbon is making 4 different bonds to 4 different atoms. But in formaldehyde, it's only making 3, it's only making bonds to 3 atoms. One of them is a double bond, but here we're talking about geometry and spatial configuration. And for those purposes, a double bond is basically the same size as a single bond. Not exactly, technically, but essentially they're the same size as a single bond. Does that make sense? Like I said, everything's building on each other. Here we go. One of the advantages of a nice and clean 3D Vesper drawing is it allows us to see the polarity of molecules. So let's remember from last time our induction arrows. So if we've got a carbon with 1 bromine and 3 hydrogens, we're going to have an induction arrow pointing toward the more electronegative element. Halogens are super electronegative. So there's our induction arrow. And this is great, but what if we have more than just one electronegative atom going on? Could have two. And in this case, we can do the same thing. We can say, all right, there's definitely an induction arrow that needs to go there as above, but there's another bromine and it's also going to have an induction arrow for it because well, it's the same bond, carbon bromine. So overall, we can actually draw just one induction arrow to show, generally speaking, what's going on. And it's going to look kind of like this. Because we've got one of the arrows going straight up, one of them going to the right. And so if anybody remembers their vector stuff from math, if we add those two vectors, we get one that points up and to the right. So the net dipole moment is a vector sum of each individual dipole, or if you like, each individual induction arrow. This case I've just shown you is just about the simplest possible case. From there, it gets very quickly more complicated to the point where you're not really drawing arrows like this. You're just saying, ooh, there's a net dipole moment and it kind of goes that way-ish. And it gets very hand wavy. But I'll show you one more concrete example, and that is ammonia. Ammonia doesn't have a halogen on it, and that's okay. Halogens give really strong dipole moments. So it's a good example up there, but ammonia doesn't. But we can go and look up electronegativities for nitrogen and hydrogen. And we find that nitrogen is more electronegative significantly than hydrogen. And so that means the arrows point toward the more electronegative element. And so we've actually got three identical induction arrows, all pointing from the hydrogens to the nitrogen. Now you'll notice that I've drawn this as a 3D structure rather than like a flat Lewis structure. I guess you could argue I should have done that up there with the bromine one. But what this allows us to see is, okay, so essentially the nitrogen, okay, here we go. Molecule dance time. So nitrogen, all the hydrogens are kind of going down, right? It's like a tripod. So if all of the dipole moments are pointing toward the nitrogen, they're all pointing up very slightly, but all toward each other. So again, if you do your vector math, the horizontal component of the vectors is going to cancel, and we're going to be left with a very small net dipole moment that's pointing vertically, straight up and down. So essentially what that means is that the top half of the molecule is more polar, and the bottom half of the molecule is less polar. How do we feel about those arrows? I'm not going to ask you to draw a ton of them or do any silly vector math, but there you go. So this whole one side of the molecule is more polar, one side of the molecule is less polar. That doesn't necessarily affect the molecule itself, but if you've got multiple molecules, like multiple ammonia molecules, you've got one side is more polar, one side is less polar, and now we're starting to see some intermolecular forces come into play. So if you remember, intermolecular forces are not what hold molecules together, but what hold molecules to other molecules. Intermolecular. So from strongest to weakest, it's funny, the strongest one that I don't know, we don't care about too much, is ionic. Try pulling that sodium away from the chloride. It's not going to happen. That's why sodium is a super reactive metal and chlorine is a super reactive gas, but you put them together and you get salt, which is not reactive at all. So ionic force is very strong, but generally in organic chemistry, we don't care too much about them. There's a big gap here between 1 and 2 compared to the rest of them. But the next most important one is hydrogen bonding. Do you remember the elements that can do hydrogen bonding? Hydrogen to nitrogen, oxygen, and fluorine. Those are the only ones. So an excellent example, of course, is water. There's water. You can draw your induction arrows if you like, and it's going to do the same thing that happened with ammonia. There's going to be a small dipole moment pointing straight up. So that means that the top part of this molecule is more polar. And so you can take another water molecule, sort of flip it upside down like that, and there's going to be hydrogen bonding interactions between the oxygens and the hydrogens. And that's going to hold those water molecules together quite strongly. And that's why water has such a high boiling point relative to other compounds that are similar to it. If you replace oxygen with sulfur, which doesn't hydrogen bond, you go from a liquid that boils at 100 degrees Celsius to a gas. I don't even know what the boiling point of hydrogen sulfide is. It's low. And it's also toxic, again, because it doesn't hydrogen bond. But so that one is also pretty easy to spot because if you've got a molecule with nitrogen, oxygen, or fluorine in it, it's going to exhibit hydrogen, well, and hydrogen, duh. It's going to exhibit hydrogen bonding to itself or to other molecules that also have hydrogens. Then there's dipole-dipole interactions, which are like the discount version of hydrogen bonding. So if we've got a polar molecule like hydrogen chloride, that has a dipole moment. Chlorine is more electronegative than hydrogen. The same way that we took the water molecule, flipped it, and it's sort of attaching to itself. Most polar molecules do that at least to some extent as well. So we have another HCl molecule here drawn the opposite direction. Dipole moment points to the left this time. And like a north and south magnet or two bar magnets, they're just going to kind of chill together like that. And so on and so forth. Notice here we're going from a solid that doesn't really melt at any reasonable temperature to a liquid to HCl just by itself is a gas. That's not a coincidence, although I'm actually going to break the coincidence here in a second. And now finally, we're at the weakest intermolecular force, and that is London dispersion forces, probably better known because it's more fun to say as van der Waals forces. So these are, this is just like, it's a catch-all category. And so increased these forces are stronger where you have molecules with higher molecular weight. Don't think that's a big surprise. Bigger, heavier molecule. And this one is also kind of hand wavy, but surface area. So if you think of a molecule as being, having a bubble around it, if you've got a giant molecule that's roughly a sphere has the smallest possible surface area for its volume, versus a molecule that's super long and skinny of the same volume that has a lot more surface area. So that's going to also affect van der Waals forces. So examples of that would be let's compare methane with a longer chain that's heavier versus a molecule that's the same size as the straight chain, but it's round. Round, relatively speaking. Methane in pentane. And the coolest name ever, neopentane. Okay. So we'll compare molecular weights and boiling points for these. Methane has a molecular weight of 16, and these two pentane isomers are both 72. They're the same chemical formula. The boiling point of methane is extremely low, minus 162 Celsius.
Wait, negative Celsius, negative freezing.
Negative 162 degrees Celsius. Yeah, for the boiling point. Should include my units. Okay, so based just so okay. these are really nonpolar molecules. There's not a big difference in electronegativity between carbon and hydrogen. We don't have ions, so there's no ionic forces. There's no hydrogen bonding because we don't have NOF. And dipole-dipole, the molecule is not polar at all, so we don't have that. So the London van der Waals forces are the only things holding these molecules together, as is evidenced by the fact that that molecule doesn't really care to be a liquid, doesn't have much holding it to the other molecules. So increased by higher molecular weight. So the boiling point of N-pentane is going to be higher or lower than methane. Higher, way higher in this case. In fact, more so than you might expect just from the size. Plus 36, so that's body temperature. Okay, then we've got N-pentane, which is long and skinny. And then this is not a... Those two shapes don't look very different from each other, but I think you get the drift. The N-pentane is long and skinny. The neopentane is basically a sphere. So based on that, is neopentane going to have a higher or lower boiling point than N-pentane? Lower. And it's not too much, but yeah, plus 10. Quite an annoying boiling point because it's a little less than room temperature. So if you want to try to work with that stuff, you have to keep it cold, a little bit cold, but anyway. So intermolecular forces. Questions on IMFs? Questions on any of the Gen Chem stuff that we've talked about? This is a pretty solid list of the stuff that's really going to be important for organic. Okay. Let's start a new page. What the heck? So we're going to go ahead and start talking about drawing of organic molecules. And I think one thing you'll notice, if I saw a lot of very frantic writing and drawing when I was drawing these, right? That looks tedious to draw, doesn't it? So for when we have really small molecules, Lewis structures or 3D structures are like reasonable to draw. So methane, you can draw that. Doesn't take too long. But as you saw up there, it gets really tedious and really time consuming to draw a big molecule like pentane, which, spoiler alert, is not a big molecule at all. So we need a way to abbreviate this sort of stuff. So the first thing we can do, which is sort of one step to where we're finally going to get for drawing molecules, is called condensed structures. So these are going to show all carbon atoms. It's not going to show bonds with some very occasional exceptions. And we're going to write in the hydrogens next to the carbon that they go with. So let's use, instead of pentane, I'm actually going to use hexane. So drawing a condensed structure for this. Well, we're going to split it up into individual carbon atoms and the hydrogens that are attached to them. So we've got a carbon with 3 hydrogens there, carbon with 2 hydrogens, carbon with 2 hydrogens, carbon with 2 hydrogens, carbon with 2 hydrogens, carbon with 3 hydrogens. So carbon with 3 hydrogens is going to be CH3. Carbon with 2 hydrogens, you see where this is going? It's going to be CH2, 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 1, 2, 3, 4 CH2 groups, and then a CH3 on the end. Let's see if we can actually make that look like a 3. Okay, that's quite a bit better already. We can keep going though. We've got 4 of those CH2 groups in a row. And so we can use parentheses to show repeating units, just like we would in a polyatomic ion that gets parentheses put around it in a chemical formula. So this here is 4 CH2 units. And so we can call it CH3 and then in parentheses CH2. We've got 1, 2, 3, 4 CH2 units all in a row. And then the rightmost CH3 group on the end. Going to switch molecules here because we need a different structure to show the next portion. Instead, I'm going to make, still going to use 6 carbons, but I'm going to make a branch. So we've got 2 carbons now coming off of that carbon there. And I'll go ahead and fill in hydrogens here. And for branches, we're actually also going to use parentheses. So I'm going to start color coding here. So we've got these 2 CH3 groups. We've got a CH just by itself. We've got two CH2 groups in the middle. And a CH3 group on the end. So to show, actually, no, let's do the CH first. Okay, so there's that center carbon of the branch. That's a CH. To the left of that, it's attached to two CH2 groups, CH3 groups individually. And so to do that, we're going to say CH3, 2. Okay, on the other side of the yellow, amber, orange CH are two CH2 groups in succession, and we also use parentheses for those. So CH2, 2. And then we've got a CH3 group on the end.
Question.
Yes.
I don't see how I can differentiate between the first parentheses and the second one, how it's branched versus how it's.
That's a good question. It is sometimes a little bit vague, but the main thing to look for there is the 3 and the 2 inside. And for this, you have to look at the valency of carbon. So I'll redraw one of the CH3 groups on the left. So there's CH3. In order for it to have its octet and to be neutral, carbon has to have 4 bonds. And so that means that there's got to be only one thing attached to it. And because it's next to the CH, it's got to be that. CH2, on the other hand, to make 4 bonds, we got to have 2 things attached to it. And so CH2 groups always have to be basically in a line of other carbons. Yeah. Okay. If you have multiple bonds, those are usually implied in condensed structures. Like we did for determining branching versus carbons in the middle of a chain, we need to use the octet rule and make sure all of our carbons have 4 bonds. So if I give you a condensed structure, actually, I won't do it the correct way. Going in the same direction that I did previously. Yeah, whatever. There we go. So this is acetone, very common solvent. Nail polish remover, we'll be using it in lab all the time. We've got a CO double bond there, and it's not in the middle of the chain, it's kind of hanging off. So just like we have so far, our CH3 groups are going to remain the same. And they're going to go on the ends, and I'm going to put something in the middle. And that's going to be that C double bond O. And as a convention, rather than writing C double bond O like that, we're just going to do CO. Because if we look at the list of carbons, carbon, 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 this carbon has 3 bonds to hydrogen and 1 bond to its neighbor carbon, that one. So it's happy. This carbon has 3 bonds to hydrogen and to its neighbor carbon, so it's happy. This carbon, even if you don't know immediately what the oxygen is doing, it's got a bond to its neighbor carbon over here, neighbor carbon over here. That's 2 bonds. So we have 2 more bonds, and that tells us that the oxygen has those other 2 bonds. You may also see it like that. That's legal as well. One of the reasons that these condensed structures are as common as they are is because they're much easier to do on a typewriter. And so when I was little, no, just kidding. Before the computer software that we usually use to draw these kind of molecules, if you wanted to publish something, nice and official looking, really the only way to draw nice looking structures was to do this sort of thing. Fortunately, the next thing we'll talk about, skeletal structures, we have software to do that nowadays. Okay. So the condensed structures are nice, but we can do better. That's a lot of, think of the number of pen strokes that it takes, that it took to write, to write this right here. Okay, let me count. I've never done this before. Let me count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That was 12 pen strokes to write the structure of acetone. To do the skeletal structure of acetone, 5. Again, I've never counted that to determine the efficiency of doing skeletal structures. But we can improve that quite a bit. So skeletal structures are the simplest kind of drawing that we have. And you may not believe me right now, but they are in fact the easiest to read. As you might be able to tell from my little drawing up there, we have omitted some stuff, like a lot of stuff. Mainly carbon, and hydrogen are not drawn explicitly. Organic chemistry is full of carbon and hydrogen, so if we can find a way to draw an organic molecule without having to draw out every single carbon and every single hydrogen atom, that'll speed things up a lot. So for our hexane, 1, 2, 3, 4, 5, 6 carbons. Promise this is the last time, other than homework, I have to draw this stupid thing out. Ugh. Okay. I got 6? Yes, I did. Okay, cool. C6H14. So we're going to draw a zigzag. And in that zigzag, each vertex and each endpoint represents a carbon atom. So hexane looks like that. Okay, so vertexes, let's look for vertexes on this skeletal structure. Come on. There's one there, 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 and there. And then endpoints, so the ends of lines that are just dangling, those are also carbons. Come on. So there and there. Other examples that are also C6H14. Vertexes here. Vertex here and here. Doesn't matter how many lines intersect, just an intersection. And then endpoints, we've got endpoints here. And all over that molecule. I know I haven't talked about hydrogens yet, but we'll get there. Okay, questions on the carbon skeletons? There's double bonds and triple bonds. They work exactly how you think they do, but we'll get there. All right, I will see you not Monday, but Wednesday. No lecture on Friday, just lab. Most of these people are in Monday lab. As in like everybody except 2 people, I think. See ya.
Oh, yeah,
You know, it's like a, still.
I didn't think that was something. Oh, let's see, it comes out.
I'm sandwiching my phone.
Oh, thanks.
I'm trying.
We think do
It was good. There was one question that I think wasn't clear.
I'll see you.
All right.
So shut up. Sorry.
You got Sam?
Is this one. The following byline needs to have an error, cross out the error and draw the full correct molecule. Oh, sorry, multiple variations may be correct.
Yeah.
Didn't read that last part. Okay. Yeah. I know exactly what you were saying. So like multiple variations, you could put a positive charge there or get rid of one of the methyl groups. Yeah, okay, that's
Yeah.
fine. The only other thing I'd say was we need to put hydrogens on that benzene.
Oh,
Is
yeah.
there another example? Yeah, on those as well, but yeah, I like it.
Yeah, my bad.
You can dance.